What if every sound you hear, your voice, a guitar string, even a whisper, was hiding a secret pattern? What if you could peel back the layers of a sound wave and see the exact frequencies that make it up? That's where the Fourier Transform comes in. It's a mathematical tool that transforms sound from the time domain, how it changes over time, into the frequency domain, revealing the tones and vibrations inside. In this video, we'll use real-time audio and Python to visualize sound as it happens. Get ready to uncover the hidden architecture of sound and see the math behind the music. Now let's see how Fourier transform of a keyboard note look like. It has a fundamental frequency about 525 Hz. Let's try violin note. It has a fundamental frequency about 525 Hz and first-second harmonic about 1050 Hz. Now, we're going to turn sound into a live frequency graph right from your microphone using Python program. Let's break it down. First, we import three powerful libraries: PyAudio to capture sound, NumPy for math operations, and Matplotlib to plot the visuals. We define a few key parameters: the sample size, format, number of audio channels, and the sampling rate. These settings control how much audio we grab and how detailed our analysis will be. Next, we open a stream to your microphone. This stream continuously listens and grabs chunks of audio data, like taking snapshots of sound every few milliseconds. Now comes the magic. We use FFT or fast Fourier transform to convert that raw audio into its frequency components. Imagine hearing a chord and instantly seeing the notes that make it up. FFT makes that possible. We then plot those frequencies using Matplotlib. The x-axis shows frequency in hertz, and the y-axis shows how strong each frequency is. Peaks mean louder tones, valleys mean quieter ones. This loop runs continuously, updating the graph in real time. So whether you clap, hum, or play music, you'll see the sound's fingerprint instantly on screen. It's a fascinating way to visualize sound and understand what's happening beneath the surface. Great for musicians, audio engineers, or anyone curious about how sound works. We can check our program works. Let's play the keyboard octave and see the frequencies. The FFT contains the fundamental frequencies as well as second harmonics. If we go for higher notes, fundamental frequency also increases. Now we're exploring the Sonometer apparatus, a classic tool used to study the relationship between the frequency of sound and the length of a vibrating wire. So what is a sonometer? It's a simple setup: a hollow wooden box with a wire stretched tightly across it. At both ends, we have bridges that support the wire and can be moved to change the vibrating length. One end is connected to a pulley and weight, which keeps the wire under constant tension. Now here's where the magic happens. When we pluck the wire or use a tuning fork, the wire vibrates and produces sound. The frequency of that sound depends on three things: the length of the wire, its tension, and its mass per unit length. Let's focus on the bridge gap, the distance between the two bridges. When we reduce the gap, the vibrating length becomes shorter and the frequency increases. That means the pitch of the sound gets higher. On the other hand, if we increase the gap, the wire vibrates over a longer length and the frequency decreases, producing a lower pitch. This simple experiment beautifully demonstrates the physics of waves and resonance. It's a great way to understand how musical instruments work and how changing just one factor can alter the sound completely. Now comes the thrilling part. Let's pluck the wire on the sonometer and watch what happens when we combine it with real-time FFT analysis. Musical notes, high voltage. As soon as the wire vibrates, our microphone picks up the sound. The Python code we saw earlier grabs that audio and instantly breaks it down using FFT, fast Fourier transform. And boom, you see the frequencies appear live on the graph. It's like watching sound come to life. Each peak on the graph represents a frequency present in the vibration. The tallest one, that's the fundamental frequency, the main pitch you hear. The smaller ones are harmonics, adding texture to the sound. Now let's experiment. We move the bridges closer together, shortening the vibrating length of the wire. What happens? The fundamental frequency increases, the pitch gets higher, and the graph shifts to the right. Direct hit. Then we spread the bridges apart, increasing the gap. The vibrating length grows longer, and the fundamental frequency decreases. The pitch drops, and the graph shifts left. It's a beautiful demonstration of wave physics in action. This setup lets us see and hear how length affects frequency in real time. It's not just theory. It's visual, audible, and incredibly satisfying to watch.